Here's a challenge for the next time you're on a highway. Find a truck, any large freight or tanker truck, and instead of looking at the cab, the trailer, or the wheels, look underneath it. All the way at the back, look at what's hanging beneath the chassis close to the road surface. There's a decent chance you'll see a chain. A metal chain just dangling there, sometimes gently scraping the asphalt as the truck moves. No one seems to notice it. Most drivers assume it fell off something. Others figure it's a piece of old rigging that someone forgot to remove. A few people who have seen it sparking at night think the truck has a mechanical problem. None of those explanations are correct. That chain is there on purpose. It was installed deliberately. It serves a function that most people, including many drivers who operate trucks every single day, have never fully understood. And when you learn what that function actually is, two things happen. First, you'll realize the chain is solving a problem far more serious than it looks. Second, you'll start seeing details like this everywhere. Small, simple-looking things on vehicles, machines, and infrastructure that are quietly doing important work that nobody talks about. This video is about that chain. But it's also about something bigger. How the world of heavy transport hides an enormous amount of engineering intelligence in plain sight. And why understanding it makes you look at the roads around you completely differently. Let's start with what makes this so puzzling at first glance. If you try to figure out what that chain does by looking at it, you'll fail. It's not connected to the brakes. It doesn't support the trailer. It has nothing to do with the suspension, the steering, or the engine. It doesn't carry weight. It doesn't guide anything. It just hangs there loose, bouncing slightly as the truck moves, occasionally making contact with the road surface. If someone showed you a photograph of it without any context, your first instinct might be that it's leftover hardware, a relic from some older design that nobody bothered to remove. And that instinct would be completely reasonable, because on the surface, that chain genuinely looks like it doesn't belong. But here's what makes it impossible to dismiss as an accident. This chain, or something functionally identical to it, appears on trucks across dozens of countries, built by different manufacturers. Operating under different regulations, carrying different cargo. The specific design varies, the length varies, the position varies slightly, but the concept is identical everywhere you find it. A conductive metal element mounted on the underside of the vehicle, positioned to make contact with the ground while the truck is in motion. When a feature appears that consistently across an entire global industry, it is never a coincidence. The heavy transport industry is one of the most tightly engineered sectors in the world. Every kilogram of unnecessary weight costs money. Every component that serves no function gets removed. The fact that this chain survives on trucks across the world, despite adding weight, despite wearing down over time, despite looking unusual, means it is earning its place every single day. The question is, what problem is it solving? And the answer begins not with mechanics, but with physics. To understand what that chain is doing, you need to understand what's happening to a truck while it moves, not mechanically, but electrically. Because while a truck drives down a highway, it is constantly generating something invisible. Something that accumulates slowly, silently, and without any warning signal to the driver. Static electricity. You've encountered static electricity in everyday life so many times that it probably doesn't feel significant. You shuffle across a carpet and touch a metal door handle and get a small shock. You pull a wool sweater over your head and your hair stands up. You peel a plastic bag apart and it clings to your hand. These are all the same phenomenon, electrical charge building up on a surface, because of friction or contact between different materials, and then releasing when it finds a conductive path to a lower charge environment. In your living room, this is harmless. The charges are tiny, the release is instantaneous, and the worst outcome is a mildly unpleasant sensation. But scale this process up to a 40-ton freight vehicle traveling at highway speed for 8 hours, and the physics of it becomes something engineers cannot afford to ignore. Here is exactly how charge builds up on a moving truck. Every time the tires rotate, and at highway speed, they rotate hundreds of times per minute, rubber meets asphalt. Rubber and asphalt are both poor conductors of electricity. When two insulating or semi-insulating materials rub against each other repeatedly, they exchange electrons. One surface gives electrons up, the other accumulates them. The material that accumulates electrons becomes negatively charged. This effect is called the triboelectric effect, and it happens with every single rotation of every single wheel. One rotation generates an almost unmeasurable charge. But a truck traveling 500 kilometers makes millions of tire rotations. those tiny increments of charge transfer add up. They accumulate in the metal frame of the vehicle, the chassis, the trailer body, the tank, because metal conducts electricity freely within itself. The charge spreads across the entire metal structure and sits there, stored, waiting for a path to discharge. But the tires are only half the story. The other major source of static generation on a moving truck is aerodynamic friction. Air is not just invisible emptiness. It is a physical medium made of molecules moving at high speed. When a truck travels at 90 kilometers per hour, it is forcing enormous volumes of air to move around its body. That air, specifically the dust, moisture, and particles it carries, rubs against the truck's painted metal surfaces continuously. This rubbing also generates charge. Not as dramatically as tire friction, but it is constant. It never stops while the vehicle is moving, and it affects the entire exterior surface of the truck simultaneously. Combine 8 hours of tire rotation on asphalt with 8 hours of air moving over a large metal body, and you have a vehicle that has accumulated a significant amount of static electrical charge by the time it reaches its destination. The truck gives no indication that this has happened. The engine runs normally, the instruments show nothing unusual, the driver feels nothing. But the charge is there, distributed across the metal structure, and it is not going anywhere on its own, not until it finds a path. Under most circumstances, a statically charged truck is not dangerous. If an ordinary freight truck, one carrying furniture, packaged food, building materials, machine parts, arrives at a warehouse and the driver opens the back door, that charge will eventually dissipate harmlessly. Maybe through the driver's body when they touch the metal handle, maybe through the loading dock equipment, a small, brief, nearly imperceptible shock at worst, nothing more. But heavy transport is not just furniture and food. A significant portion of what moves on the world's roads is flammable: gasoline, diesel, jet fuel, liquid petroleum gas, industrial solvents, ethanol, chemical reagents, paints. These substances are transported in huge quantities every single day in specialized tanker trucks to fuel stations, airports, chemical plants, and industrial facilities around the world. And flammable liquids have a property that makes static electricity genuinely dangerous. They evaporate. Even in a sealed tank, fuel vapors accumulate in the space above the liquid. When a tanker is being filled, when it's being unloaded, when a hose is being connected or disconnected, those vapors are present in the immediate environment. They mix with the surrounding air. And when a flammable vapor mixed with air reaches the right concentration, which engineers call the flammable range, it becomes a gas mixture that can ignite from any energy source. Any source at all. It does not need a flame, it does not need a hot surface, it does not need a cigarette or an open fire. A spark, a single electrostatic discharge, carries enough energy to ignite a fuel-air mixture if the concentration is within that flammable range. And the energy in an electrostatic discharge from a vehicle that has been building charge for hours can be more than sufficient. This is not a theoretical risk invented by overly cautious engineers. It is a documented cause of real incidents in the transport industry: fires during refueling operations, ignitions at fuel depots during unloading. Events that happen not because of equipment failure or driver error, but because a charged vehicle connected to conductive equipment discharged. And that discharge found fuel vapor at exactly the wrong moment. The scenario that engineers worry about most is not while the truck is moving, it's the moment the truck stops. After hours of generating and accumulating charge, the vehicle arrives at a fuel depot or service station. The driver steps out, picks up a metal refueling hose, and connects it to the truck's inlet. That hose is conductive, the dock equipment is conductive, the ground is conductive, and suddenly the truck, which has been storing charge for the entire journey, finds a path. The discharge happens in a fraction of a second. If fuel vapors happen to be present at that connection point, which they very often are during refueling operations, the result can be ignition. The problem from an engineering standpoint is that you cannot prevent static electricity from forming. The friction of tires on road and air on metal are simply physical realities of a moving vehicle. You cannot eliminate them. So if you cannot prevent the charge from being generated, what can you do? You prevent it from accumulating. The fundamental insight behind the chain is elegantly simple. If you give the electrical charge a way out while the truck is moving, it never reaches dangerous levels. Instead of allowing hours of generation to stack up into a large accumulated charge, you bleed it off continuously. a little at a time, constantly, throughout the entire journey. By the time the truck arrives and connects to anything, there is almost no charge left to discharge. The risk is reduced to near zero, not by preventing generation but by preventing storage. The chain makes this possible by doing one thing. It creates a conductive path between the truck's metal frame and the ground. As the chain drags along the road surface, even intermittently, even lightly, it creates electrical contact between the vehicle and the earth. And the earth, in electrical terms, is the ultimate destination for stray charge. The ground is a virtually infinite conductor. It can absorb enormous amounts of electrical charge without any measurable change to itself. Electricians and engineers call it ground for exactly this reason. It is the baseline, the 0 point, the place all charge eventually wants to reach. When the chain makes contact with the asphalt, the charge accumulated in the truck's chassis flows down through the chain and into the road surface, and from there disperses into the earth. This happens continuously as the truck moves. The chain drags, contact is made, charge flows. The truck's electrical potential drops toward zero, more charge builds from the tires and air. More charge flows out through the chain. The system reaches a kind of dynamic equilibrium where buildup and discharge happen at roughly the same rate, and the net accumulated charge stays very low. The elegance of this solution is that it requires absolutely nothing from the driver. There is no button to press, no system to activate, no procedure to follow. The chain does its job the entire time the truck is in motion, without any input, any power source, any electronic component, or any maintenance beyond occasional inspection for wear. It is a passive system in the purest sense. It works by existing, by being in the right place, by being made of the right material. And the material matters. The chain must be metallic, a good conductor, so that charge flows freely through it. It must be long enough to maintain contact with the road surface, even when the truck body flexes slightly at speed or on uneven pavement. It must be mounted at a point on the chassis that is electrically connected to the main metal structure of the vehicle. Get these three things right, and you have a functioning static dissipation system that costs almost nothing, requires almost no maintenance, and works continuously for the entire operational life of the vehicle. There is something almost philosophically satisfying about this. One of the most important safety systems on a vehicle carrying thousands of liters of flammable fuel is a piece of chain. Not a computer, not a sensor array, not an active management system, a chain dragging on the road. It works because physics is consistent. Electricity always flows toward lower potential, and the ground is always at lower potential than a charged vehicle. The chain just creates the path. The chain is not the only solution to this problem. It is the oldest and most visible one, which is why most people notice it first. But over the decades, as vehicle design has evolved and manufacturing standards have tightened, the industry has developed alternatives that perform the same function in different ways. The main limitation of a traditional metal chain is consistency. When a chain drags on asphalt at highway speed, contact is not perfectly continuous. The chain bounces. At certain speeds, it can briefly leave the road surface entirely. On smooth, freshly paved roads, the chain may not drag heavily enough to make reliable contact. On rough surfaces, it can wear faster. None of these are catastrophic problems. The chain still works, but they represent imperfections in an otherwise reliable system. Modern alternatives address these imperfections. One common solution is the conductive rubber strap, a flat strip made of rubber that has been manufactured with conductive carbon particles embedded throughout the material. This strip is mounted on the underside of the chassis and drags along the road surface like the chain does, but with more consistent contact because of its flat profile and greater surface area. It also produces far less noise than a metal chain and wears more evenly. Some manufacturers have moved to conductive polymer elements, specially engineered plastic-based materials with precisely controlled electrical resistance. These are designed to bleed charge off at a specific, controlled rate. Too much resistance and the charge doesn't dissipate fast enough. Too little resistance, and the discharge happens so freely that it could potentially cause issues in other electrical systems connected to the chassis. The engineered polymer hits a specific target in the middle, enough conductivity to keep the vehicle's charge near zero, not so much that it interferes with anything else. Other modern trucks integrate static dissipation directly into the tire compound itself. Tire manufacturers working with truck producers have developed rubber formulations that are slightly conductive, not enough to cause any electrical issues with the vehicle's systems, but enough that charge generated at the tire road contact point flows back into the road immediately, rather than building up in the vehicle's structure at all. This approach eliminates the need for any hanging component under the truck entirely. This is why, when you look at a modern tanker truck on the road today, you may not see a chain at all, and yet the vehicle is still managing static electricity. The system is there. It has simply become invisible, integrated into the design of the truck rather than hanging visibly beneath it. The problem hasn't gone away. The solution has just gotten cleaner. There is also a regulatory dimension to this. Different countries and industries have different standards for static electricity control in fuel transport. In some jurisdictions, there are specific requirements for what type of dissipation system must be installed on vehicles carrying certain categories of flammable material. In others, the standard is performance-based. The vehicle must demonstrate that its electrical potential stays below a certain threshold during operation, without specifying exactly how that must be achieved. These regulations have driven a lot of the innovation in this space, pushing manufacturers towards solutions that are more reliable, more measurable, and more integrated than a hanging chain. Here is what I want you to take away from everything we've just covered, and it's bigger than the chain itself. Every truck you pass on the highway is a machine that has been engineered to a level of detail most people never think about. The chain under the tanker, the specific rubber compound in the tires, the shape of the fuel inlet, the grounding straps at the loading dock, the procedures the driver follows during connection and disconnection. Every single one of those details exists because at some point someone asked a hard question. What could go wrong here, and how do we make sure it doesn't? That process, identifying a risk that is invisible, understanding the physics behind it, and designing the simplest possible solution that neutralizes it, is what engineering actually looks like in the real world. It almost never looks dramatic. The chain doesn't look like a safety innovation, it looks like a piece of forgotten hardware. But it represents exactly the kind of thinking that keeps millions of tons of flammable material moving safely across public roads every single day. The roads are full of details like this. The raised reflective lane markers that were designed with a specific shape, so that rain washes them clean automatically. The slight camber built into highway surfaces, so that water runs off the edge rather than pooling. The specific weight limits posted on bridges, calculated not just for average load but for the worst combination of factors: maximum payload, maximum speed, maximum vibration frequency that could create resonance. The color coding on fuel hoses at depots so that the wrong fuel cannot be accidentally connected to the wrong tank. None of these details are visible in any obvious way. All of them are engineering solutions to real problems that someone worked through carefully. The chain under the truck fits perfectly into that tradition. It is a solution to a problem that most people don't know exists, using a mechanism that most people don't understand, doing work that nobody sees. And it does that work every kilometer, at any speed, in any weather, without ever needing to announce itself. There is a lesson in that for how we think about the world around us. The things that look simple are often solving problems that aren't simple at all. The components that look unnecessary are often the ones doing the most quietly critical work. The next time something looks out of place, on a vehicle, in a building, in a piece of infrastructure, it's worth asking, why is that there? Because more often than not, the answer is more interesting than you'd expect. The roads connecting our cities are more than just asphalt and painted lines. They are a system, a vast, continuous, carefully engineered system, and the trucks moving through that system are not just vehicles. They are machines built to solve dozens of invisible problems simultaneously, at speed, for hundreds of thousands of kilometers over their operational lives. That chain dragging under the tanker is part of that system. A small part, an easy-to-miss part, but a part that is doing exactly what it was designed to do right now on roads all over the world. If you found this interesting, if you like understanding the hidden engineering logic behind things you see every day, subscribe. Every video on this channel starts the same way, with something ordinary, something most people never look at twice, and asks the question that makes it extraordinary. There are a lot more of those questions waiting. We'll get to them.